said, let's look at the packet. Let's look at the packet first. So what we want to do is kind of two parts today. The first part is to just make sure we are feeling comfortable with the notation on definite integral. All right, finding a piece of area. Then we're going to move into the next level. We're going to start talking about it as a function. We're going to start talking about working our way to what can we think of the integral. You look at what we have over here on the board. Develop an understanding of the integral as a function. Right now, the integral is just a piece of area. It's just a number, okay? And we want to get that way, just like with slope. When we first talked about slope of a curve, it was just a number. It was, you know, how steep the curve was. But then we got into derivative as a function and got into all those formulas and so forth, so on. And that's where we want to head. And over the course of the next several days, we're going to develop that. And it's pretty cool how it all kind of comes together. But we've got to understand the notation, and there's a lot of that. And the notation's harder than it is with derivative. I mean, what notation is there for derivative? F prime. And the little prime symbol, that's it. I mean, that's not very hard to comprehend. With the integral, there's a lot more to it, this whole dx thing and the integral symbol and so forth, so on. So it is a little more involved. So this first part was really just that. This first part here was just setting up the integral. And some of you even asked me, said, really, is this all I had to do? I mean, for example, in this first one, it's literally, that's it. 3 dx 0 to 5. Understanding that here's the function. We're doing the area under that from 0 to 5. That's it. Now, don't forget the dx. Okay? This one over here, integral 4 minus 2x dx from 0 to 2. That's it. That's all there is to it. Okay? And so forth and so on. Now, we skipped 6 and 7. And so I want to spend just a little time talking about that actually here. Because there is something going on here that we will be getting into more later. So I'm not going to make a big deal about it. But I do want to show you how there's a little more to just these areas than where we're at right now. What do you notice is different about the picture on 7 compared to all the rest of those pictures? The area does not go to the x-axis. It goes to the y-axis. Still an area. Actually, notice the function is given in kind of a strange way, too. Instead of f of x equals tangent x, which we know is the same as saying y equals tangent x, right? They say g of y equals y cubed. What do you suppose g of y is the same as? It is. That's the same as saying x equals y cubed. Well, if you would solve that for y, you get y equals cube root of x, and that's exactly what that function is. That's the graph of cube root. The other tail on the cube root would go off this way. That's the cube root function, like that. Okay? But what they did is they wrote it, instead of writing it in terms of x, they wrote it in terms of y, because they wanted to do the area with the y-axis, and we actually can do that. Okay? That is, and now why would you want to? Well, there will be some applications we will see down the road where we will want to talk about this region as opposed to this region. And so that is, and that can be done. And so what would be this integral? Just what do you think would be different? Well, what would go in here for my function? Y cubed. What do you suppose would come after it? dy. That's right. And what numbers do you suppose would go here? 0 to 2. Perfect. Because now you're doing the area this way. Okay? So it'd be the area from 0 to 2. Now, let's have somebody, let's see here. Let's pick somebody to be our presenter here. This is really going to bog down the system, I think. But we got some people not logged in yet. Nice try, Heather. Oh, wait, I'm not going to pick on Heather. She was on yesterday. She's going to be lucky to take some notes here. Who else is not logged in? Jacob Rolla. You logged in? Well, he might be. I just haven't refreshed my screen. There he is. All right, Jacob. You are a presenter. So, go to the calculator screen, please. And everybody else can do this too. We're going to do an integral on here. Okay, if you haven't already discovered, and I'm sure you figured it probably would, but go to the same place. Okay, go to the same place you would go to do your derivative. You go to the template screen, and there's two integral symbols. We want the one that's got the a and the b on it, those two right there. So we want that. That's our definite integral. And let's put in our 0 and our 2 here. And let's put in our y cubed. Okay, and then dy, and hit enter, and we find that that area is 4, okay? And so this will do these definite integrals for us. Now, our first quiz, though, is going to be no calculator. So, I was helping somebody this morning, and we were talking about, I said, draw a picture, draw a picture. So they reached in their bag, got their calculator out, and started drawing graphs. No, you're going to have to be able to draw these graphs of these basic functions. You're going to have to be able to draw them without a calculator, okay? So now let's talk about this a second, because we were just back here looking at this thing, and he just showed us that this is 4, and that, I'll buy that. That seems reasonable that that would be an area of 4. But then I'm reminded of the ones we were talking about yesterday on our homework. When we were doing integral, remember we said how the letters here didn't really matter? Remember if this was u cubed or w cubed or z cubed, it didn't matter, right? So shouldn't this integral be the same as this right here? Shouldn't those be the same? Now, okay, what do you mean by the same? Should these two have the same value? Yes. So if Jacob, go ahead and do that, Jacob. Go back to your calculator and type it in again, except use x's this time. And and then we can have him do W's and Z's and everything else, and it wouldn't matter. We're going to notice that we're going to get 4 every single time. Okay? And so there's his 4. Now, but do these two mean the same piece of area? No. This one would be the graph of y equals x cubed, which would go up like this from 0 to 2. And that would be that piece of area, but doesn't it make sense that those are really the same? They're really the same, they're just kind of flipped. They're really inverse functions, if you will, of one another. And so they are the same definite integral. They don't necessarily represent the same piece of area, but they are the same value. And that is important to understand. Yeah. Okay. Yeah. If you put a dy there but had x here, yeah, then, well, here's what it would do. Well, I don't know. Let's try it. No. It wouldn't. And I'm not even sure what would happen. Put a y in there. I think you'd, yeah. It would just treat this as a constant. And so it thinks this is the graph of, it thinks x cubed is this horizontal line from 0 to 2. So it'd be 2 wide and x cubed tall. And so it'd be 2x cubed. And that's why the calculator did that. So, because you're telling it y is the variable, so it treats everything else as constant. So, yeah. So we'll get into that. We're going to get into, actually, number 71 got into something like that, where you've got different functions going on, and we're going to talk about that problem as well. Okay. All right. So let's go back. Let's go back to this, and so that pretty much takes care of those questions. Let's take a look at the bottom then of this, and I wanted to talk about number 15 because I did help a couple people and they did some kind of interesting things. I guess before we do 15, let's talk about these bottom ones. Now, also had some questions in the other class about these with the A and the R in them. They just connect to these. For example, on 17, did somebody want to explain to me what they would do on 17? Did you draw a picture? I guess my question is, did you split this apart, or did you just draw a picture of this? Okay, now this is interesting because I would never have thought of splitting this apart, but then it dawned on me when somebody asked me about splitting it apart. I said, oh, I guess yesterday we did make a big deal about splitting them apart, didn't we? We talked about doing it. Now, to be honest, the only time you really need to split them apart is if there's part of it you do know how to do and maybe another part you don't. Like, for example, we had the x squared as part of one yesterday. We didn't know how to do that area, but they told us the area. So I wanted to split it apart so I could substitute. But on this one, isn't this just a V graph upside down and up one? So to be honest, most of the time but splitting it apart is fine. That works just fine. But I have a feeling it might be easier just to do this, but it's up to you. So if we did this, we shifted up 1. From -1 to 1 is where it crosses. Here's your area. It's a triangle. It's 2 wide, 1 tall. That'd be 2. Half of that would be 1, right? Well, if you do it with A, isn't this the same thing? Just shift it up A. So it's flipped upside down, shifted up A. This would be -A to A. So it would be a triangle. It'd be 2A wide, A tall. That'd be 2A squared. Half would be just A squared, right? Yeah, right. So you still get the same thing if you split it. And I didn't even think about doing that. And I wanted to talk about that on 15, and I'll show you that. This is a half circle with radius 3, so that would be 9 pi. But then you got to take half of it, right? So radius 3 be pi r squared, it'd be 9 pi, take half that's the top half of the circle. Well, this one would just be the top half of the circle with radius r, so it would go -r to r. And so that's what your integral is, -r to r, so half circle, or circle's pi r squared, you take half of it. It would just be pi r squared over 2. The cool thing is, on our calculator, actually, Jacob, why don't you go ahead and type that in for us, because it is kind of neat to see. The calculator will actually do that. Remember I said that anything that's not the variable, it treats as a constant. So do your integral again. And let's go -r to r. And then here do square root. And let's do r squared minus x squared. And then we'll do, and then dx. And so you're telling it x is a variable. It knows r's are variable. And then it does this. Now that's interesting. Why did it do that? I'm not even sure why it does it, to be honest with you, because since you're doing r squared, what they're saying is r is positive. R needs to be positive here. We need to tell it that r was positive. Well, if r,
because that could be the bottom half.
well, no. Well, we did, because this is positive square root. So that would specify that it's top half. But if r is negative, yeah. Oh, you know why that would be? Here's why that would be. Because if r is negative, then which one of these is backwards? If r is negative, then negative r is actually positive. This would be going from positive to negative, which is backwards. And if you go backwards, the top half of the circle is negative area, right? And that's why it's doing that. So arrow back up to that and hit enter. Yeah, hit enter. And let's do vertical bar. No, at the end of the dx. Go all the way in. Vertical bar. And then let's, whoops, that's parentheses. Vertical bar is up here. You got it? And then do r greater than 0. Okay, and then we get that. Okay, so we can put that condition on it. Okay, so good. So I didn't really think of it that way. We're assuming r was going to be positive. That's the way we drew it. Okay, good stuff. Now let's. I want to talk about 15 here a minute. I've got, and I want to show for those of you that are wondering what we're talking about with the splitting it apart. Here we go. Okay, so here I've got 15, so I got 2x plus 5. Now, when I would do this, I would think of the 2x plus 5. I think that's the way you're normally going to think about it. You're going to think of that as the function you're doing the area under. So you're going to graph that. So you're going to go up 5. You're going to go up 2 over 1, up 2 over 1. Okay? You're going to draw yourself this line, like so, and you're going to do the area from 0 to 2. So that's going to be this red area. Okay? So that's the area we're looking at. Well, we could just count squares, whatever, but it's a trapezoid. So that's 1/2. What's this height here? 5. This one over here is 9. That'll be 5 plus 9. And then your base down here is 2. So 14 times 1/2 times 2 is 14. Right? That's our area. But I could see somebody doing this because we talked about it yesterday. We made a big deal about it. We said you should split this apart. Now you can split it apart. Whether you should or not is a whole other story. We talked about pulling the 2 out in front. So you can do that. You get x dx plus, right? This is perfectly fine. It's okay. Probably a little unnecessary, but it's fine. So now the function you'd want to graph is y equals x. So you'd come over here and you graph y equals x. Oops. You're going to do that area from 0 to 2, which is going to be this triangle, which is a 2 by 2. What's that? 4, half that's 2. So this whole thing would be 2. 2 times 2 is 4. This would be a horizontal line. This would be y equals 5 from 0 to 2. 5 times 2 is 10. 4 plus 10 is 14. So you do get the same thing. Okay? So yeah, if you did that, because I did talk about how splitting it apart is a good strategy, usually it's a good strategy if you're stuck and can't graph the original. But if you can just graph the original, you'd have that in the red. Okay, so that's good stuff too. Why do we have this one? This one you have a question on? Do we do that one? 62? 66? This 62? Okay. All right. And think about this. Think about these questions now, the ones in the book now we're talking about. Think about these as if the quiz were tomorrow and these were potential quiz questions. Could you answer these, right? That's what we should be thinking. Now, on this one, it would have been helpful, first time you're seeing this on your homework, to have flipped back a few pages. I think the actual page is 307, actually. If you flip back to page 307, you see that they have an example that talks about bounding an area. So the idea here is, if I would graph this, again, this is the part I was still a little disappointed on. I looked at 62 on some of your papers, didn't see a picture. I looked on, I'm thinking of 57's another one that I think could be an interesting one, and I didn't see a lot of pictures in that range. I think you need pictures here. So first thing I think somebody ought to do on one like this is draw a picture. Now let's divide this up nicely here. Let's make that be pi. So this first one would be pi 6. That would be pi halves, because we're going from pi 6 to pi halves. So this would be pi 6, 2 pi 6, 3 pi 6, 4 pi 6, 5 pi 6, 6 pi 6. If I graph the sine curve, let's go up here. About is our 1. So sine would go here. At pi halves, it would be at a peak. Pi would be back here. So here's our sine curve, something like this. And so we're talking about the blue area is the area from pi 6 to pi halves. It would be this area right here. Now, I have no idea what that area is. It's not a trapezoid because this is curved on top. So it's not a trapezoid. I don't know what that area is. But what they're saying is, can I show that the area has to be between these two? Right? Well, if you look on page 307, what it does is, what it suggests is use the idea of max and min. Now, this is a simple one, but we learned in chapter 4 how to find the max and min. If we've got a closed interval between pi 6 and pi half, we know that there has to be a max value and a min value. We can find them. Wouldn't it be true that if you took the minimum value, and let me do that in red, and of course in this one it's going to be at the left edge since this graph's increasing all the time in between there. The minimum is at the left edge. And if I drew straight across, I know that the graph goes higher than that because that's the minimum. So I know there's actually more area than that red area. And then if I took the maximum, let's do that in green, and went straight across from that, I know that the actual area is below that, or at least it could be that, but it would have to be that or less. Wouldn't it be true that the blue area would be trapped between those two? Right? So it's using the idea of minimum and maximum here. Right? Well, now, and so that's the part you wouldn't have known what to do. You wouldn't have thought of doing that. Probably. Okay? Without having seen it before, or maybe looking at that example. Now it's just a matter of doing that calculation. So the red area is just a rectangle. How tall is it? What is this y value right here? And root 3 over 2? It'd be sine of pi 6, wouldn't it? This is the sine curve. So it'd be sine of pi 6, that's 1/2. So the height of that rectangle would be 1/2. And what would the width be? Well, it'd be the distance from pi halves to pi 6. What's pi halves minus pi 6? Pi thirds? That'd be 3 pi 6 minus 1 pi 6. That'd be 2 pi 6, which is pi thirds. So this gap here is pi thirds. Sure enough, 1/2 times pi thirds would be pi 6. So we know the red area is pi 6. And likewise, the green area would have a height of 1 and a width of pi thirds. So 1 times pi thirds would be pi thirds. And so sure enough, we know that the blue area, and we've shown with our picture and our calculation, that the blue area has to be between those two. Okay? But it's using the idea of minimum and maximum. That's not something you're going to see a whole lot. I mean, it could show up. Again, that feels to me a little bit like one of the midterm kind of problems, right? A packet kind of problem. Kind of thing you don't see that often, but you got to pull in some various things you've learned. Okay? All right, what else? 66. What was 66? That's 71. 66. Oh, yes, average value. Good question. Okay? This one says that the average value from 0 to 1 is 2, and the average value from 1 to 3 is 4. Well, every person I helped with this that was stuck didn't have anything on their paper, right? Well, where do you start? The formula, right? Yeah, it says the average value is. So write out the formula I gave you yesterday for average value. So the formula was integral, integral from a to b of f of x dx over b minus a. So the first one they told you was the average value from 0 to 1 was 2, right? And they told you that the average value from 1 to 3 is 4, correct? So write out the formula, okay? Now, they wanted to know the average value from 0 to 3. Well, the average value from 0 to 3 is this. Right? So I've written down what they gave me, and I've written down what they want me to find. So let's do it. So what's the only thing, what don't I know that I need? I need the integral from 0 to 3. Is there any way from this I could get that? Not quite. I got to do something first. So yes, because if I knew the integral from 0 to 1, and I knew the integral from 1 to 3, add those together, that's the integral from 0 to 3, right? So first I need to multiply, well, this is 1 times 0, that's just 1. So multiply that over, so that doesn't matter. 3 minus 1 is 2, so multiply that over, make that be 8, right? So the integral from 0 to 1 is 2. The integral from 1 to 3 is 8. So that means the integral from 0 to 3 is 10. And then over 3. 10/3 is my average value. The average value from 0 to 3 is this formula here. So I needed the integral from 0 to 3, which I just got, or the integral from 0 to 3, which I just got to be 10, so it's 10/3. So the average value is 10/3. Okay? All right. I mean, notice it wasn't just an average, right? We had an average value here was 2, the average value here was 4, the average value between those is not just the average of those two numbers. Kind of somebody shoots 50% free throws and somebody shoots 100% free throws. What is their average together? It ain't 75. Unless they happen to have shot the same exact number of free throws, right? If I'm 100 for 100 and somebody else is 1 for 2, right? The two of us together is not 75%. We're 101 out of 102. That's much better than that, right? They're disproportionate. This one went from 0 to 1. This one went from 1 to 3. And you don't know how those went. So you can't just average. Yes?
Wait, so why don't you just do the cancel thing?
What do you mean the cancel thing?
Like the one where you go the integral 0, 1, and then the other one's integral with the 1 on the bottom and the 3 on top.
That's what we did. Yeah. So, okay. So I had the average value thing written out here. Yeah. Okay. But it wasn't the integral that was 2, it was the average value that was 2, right? So I multiplied the 1 over to this side, which...
I guess I just forgot the dividing part.
Yeah, you forgot the dividing part of the formula, I think. Because the average value formula is this, right? Yeah, so we multiplied the 2 over there times the 4 and got the 8. So what that gave me is this integral is 2 and this integral is 8. So then what I did is that canceling part. This plus this makes that. 2 plus 8 is 10, but that's, yeah, you're right, that's just this part. You were forgetting the dividing part. Okay? Yeah, that's important because that's average value of a function. The integral's part of it, but it's not the whole thing. You got to have the dividing part of it. Okay, what else? 71 will do for sure because I want to talk about that. Let's look at 57 maybe. Okay, I saw a lot of question marks by 57. I also saw some people with answers written down with no real supporting work, and I have a feeling that was a lot of just looking in the back of the book because I'm not sure how you get it otherwise. If you go from 0 to pi halves of x plus cosine x dx. Now, here's the part a lot of you were missing. I don't know why I don't have my grid there. They told you in the directions that the integral of sine from 0 to pi was what? They told you that was 2. Now that is a really important piece of information right there. They told you that the area under this hump, and that is not a half circle, by the way. Okay, there's people wondering. That is not a circle. Okay, that hump area is 2. Think about what you know about sine and cosine. What do you suppose this area is? It's going to be the same, except negative, right? What do you suppose on the cosine graph the area of that hump is? Also 2, right? Because isn't the cosine curve just the sine curve shifted? Right? It is. So they're the same. So that was the real key to doing these problems. All right, so now you were supposed to do this. Well, where did you need to start with this thing? Split it apart. And so this is what I was looking for in people's papers, and I wasn't seeing it on a whole lot of them. This should have been written like this. Okay? Now, this one is simply the right half. Let's do it in red. That's just the right half of that hump right there. So it's got to be 1. It's got to be 1. That's how we know that is 1 right there. And then this one, we simply have to draw the graph of y equals x. This is just what we've been doing now for a couple of days. So we draw the function y equals x. We go over here to pi halves, and we do this area here. It'd be a triangle. How tall is that triangle? Pi over 2. So it's pi over 2 times pi over 2, and then it's times a half. What's that? Pi squared over 8, and then add on the 1. So it's pi squared over 8 plus 1. And that's how the back of the book has pi squared over 8 plus 1. We split it apart, and we use what they told us about the sine curve and what we know about sine and cosine kind of being the same graphs, as far as just shifted. And so therefore those areas have to be similar. Now what we don't know, and what we will be learning over the course of the next several days, is how in the world they got 2 for that area, right? Because there's no geometric formula for that. How in the world are we supposed to know that that's 2? That's what we're going to be getting into over the course of time. All right, let's go back to number 71, which is this one here. Now again, you need to be able to draw these pictures. You got the line y equals x. That's a pretty bad line, but it's good enough for what we need. And you got the graph y equals x cubed. Now I've graphed them with little different scales here because I wanted to be able to see this area nicely. But let's read this question. They give you these two functions f and g. First they say sketch the region in the xy plane bounded by the curves f of x, g of x, and the line x equals 0. Now where's x equals 0? The y-axis. So isn't that this blue area right here? This is the area they're asking for. Now this is something we haven't quite seen before. It's kind of similar to the one I showed you in the LH packet. The area is with the y-axis, not the x. But the difference is it's along 2 different curves. It's not just a straight line to the y-axis or a straight line to the x-axis like we're used to. It's bounded by curves of more than one. Well, that's something we're going to get into in chapter 7, actually. But I think we could get a little bit of a preview of that here, and that's what part B is about. Part B says express this area using integrals. Well, the only way we know to do integrals right now is to do the integral of a function. So let's do this function first, the red one. Let's do the integral of x plus 6 dx. Now, what area up here would that be? Somebody want to sketch it? Sketch that area. Oops. Sketch that area in red. She didn't know what she was volunteering for when she volunteered. Pretty good. Okay, that is good. All right, now in green. Now, oh, and by the way, that integral would go from where to where? This point of intersection is important. You would have to find that point of intersection. It's 2, 8. If you put a 2 into this, you get 8. Put a 2 into here, you get 8, right? So that's a key point we'd have to find it. Okay, so this would be the integral from 0 to 2. Now in green, let's do the integral of x cubed dx. Somebody want to shade that for me? I have a new appreciation for my drawings here. But all right, you know it. We know what you mean. So we're talking about this area here. Okay? All right, practice. All right, so that's the green. And that is also from 0 to 2. How do we get the blue from those two? Red minus green. And so that integral right there is what they were, or integrals is what they were looking for. To get that blue area, we could take that red area, the area under the F graph, minus the green area, which is the area under the G graph. Now, in the back of the book, they probably said f of x minus g of x, I'm guessing, or g minus f, whatever. Okay, but that doesn't mean a whole lot. I mean, that'd be correct, but here's what we're talking about. Now, let's take that one step further and let's connect that back to something we were talking about when we were doing that x cubed, y cubed thing. We were talking about how they were the same value, but they were different pieces of area. Let's talk about this in this scenario. So here we got this blue piece of area, which is the area between these two graphs and the y-axis. But let's take a rule we learned yesterday and actually last week that said if you can split apart two integrals, yeah, don't suppose you could put them together? And we can. We should be able to put this integral together, and Jacob, you're going to be up here shortly again on your calculator. We could put this together into one integral. Now, if I think of this as just one integral, if I forget all this other stuff now, if I just gave you this integral and told you to draw a graph of the function that we want to do the area under, what function would you graph? No, would you split them apart? 2x plus 5, do we split that apart? No, we just graph 2x plus 5. What could we graph to do this integral? That function right there. That wouldn't be either one of these functions. That would be a whole new function unto itself. So, Jacob, let's go to your calculator here, and let's graph that function. Go to your graph screen here. Go to your graph screen, and let's, what are you in parametric? Let's delete that. Let's go to, let's go to function mode. We want to go to function, okay? Graph entry. No, graph, you were right. Function, there you go. Okay? And let's put in x plus 6 minus x cubed, because that would be a function unto itself, right? As opposed to two separate functions. Okay? Now let's go to our window, and let's set the x from, say, 0 to 3. And let's set the y from, say, -2 to 10 would be fine. Yeah, he's still got that parametric, but that's okay. So here's 2 in here somewhere. Okay? Here's, what's that, 3 way over there? Actually, 2 is right there. Yeah, 2 would be right here where it's touching. So this area right here, what do you suppose that area is? The same as, well, right, it would be the same as this blue area here. They're two totally different pieces of area, two totally different shaped things, but their integrals would be the same. In other words, they would have the same value. They would have the same amount of area, and that makes sense. I mean, if we get an integral and the answer comes out to be 10, there could be infinite number of different shapes that could have an area of 10, right? So just because this definite integral just represents, in this case, we came up with it representing this blue area, but this integral could also represent the area of the picture here on Jacob's calculator right here, this area in here, okay? So, just something to keep in mind as we're setting up these integrals and as we're working with them. Okay, I think that's about all I necessarily had, unless somebody's got something else. 38, make sure you understand 38, where it's talking about velocity. Basically, that talks about what we did yesterday when it came to net distance traveled, displacement, as opposed to total distance traveled, right? The area under the velocity curve was the net distance traveled. The area under the speed is the total distance traveled, okay? And that's important. And then the averages, it talked about the average value. Well, your average velocity is a lot different than your average speed. For example, and this is what happened in that. If I'm standing here, and I go for a while this way, and I go for a while this way, and I end up right back where I started, what's my average velocity? 0. Because I had positive velocity and negative velocity, and the average of that, when I end up right back where I started, is going to be 0. But what about my average speed? How far you get? But it wouldn't be 0. Right? The only way your average speed is 0 is if you never move, because speed is always positive. So the only way you can do an average of positives or greater than or equal to 0, right, and get zeros if they're all 0, right? You can't, so you didn't move at all. But average velocity is based on direction and all that stuff. Okay, so that's an important difference, and that's what 38 was about. So it's important that we understood that. All right, let's move on to, let's see, not that yet. All right, we're going to spend a little bit of time with an activity here today where we're going to take that next step now. All right, so we've been talking about area. The definite integral gives us this area. We can do some very simple ones like with geometry. We've also seen how we can get into some more complex thoughts and ideas on areas using this integrals and understanding the notation. But even with that said, almost everything we were doing there, the answer came out to be a number. Even the one that was pi squared over 8 plus 1, that's a number, right? Now we want to get into the idea of a function. So it's like we're moving from where we find just the slope at 4 to where we find the derivative function of what's going on. That's what we want to do. Now, so that's what we're going to get started. Now I've got a thing I'm going to send you on your calculators here in a minute. But let me just show you kind of where we're headed with this. Now it relates back, as many of these things do, to something we did earlier. Okay? When we were first developing slope as a function, we did this right here. Hopefully you remember. Okay? And if you do, make sure and tell Mr. Madsen, yes, Mr. Clark, of course we remember. So what we did is we graphed the sine curve. Okay? And we said, let's look at the slope of the sine curve at different places. So we said, what about when x is 0? And you remember what the slope was? It was 1. And then we said, let's go to, I don't know, pi fourths. What's the slope? Less than 1. It was about 0.707, something like that. Then let's go to pi halves. What's the slope? 0. And then let's go to 3 pi fourths. And what's the slope? That'd be over here. Negative 0.707. There you go. And then at pi, what's the slope? Negative 1, and so forth, so on. And we kept going, and we said, let's treat that as a function. Every function has an input and an output. So what our function's going to have is x is going to be where we're calculating the slope, and the y, the output's going to be what the slope is at that point. We'll call that the slope function, right? And so we said, let's plot that. So we plotted the point 0.01, and then the point pi fourths, 0.7, and then pi halves and 0, and then 3 pi fourths and negative 0.7, and then negative 1, and what did we end up with? We ended up with the cosine curve, and it was like, wow, that is really cool. You mean to tell me, because I remember you said that, I know you did, that don't lie, don't try to be cool now, all right? But what we found out was the slopes, right? The slopes of the sine curve actually was the cosine curve. It actually was the y values of the cosine curve. And so therefore from that we got the formula, right? The derivative, if f is sine, then the f prime graph was cosine. So derivative functions are really that. They're the slopes of a graph. All right. Well, we're going to do that same thing now, but we're going to do it with area. We want to treat area as a function. Now, one of the first difficulty there is we can't do area at a point, right? We can't let x be the point where we're going to do our area, because area has to be between 2 points, right? We have to do the area from here to here. So what we're going to do is we're going to fix the left point, and then we're going to move the right edge. And every time we move the right edge, we'll get a new area. Wouldn't that make sense? Right? So if I had a function, well, it looked like this. Let me show you. So if I had a function, we'll just start with some whatever. This is some function f. And so let's say we'll just start at 0 to make it easy. So we'll do our integral. We'll make the left edge be 0. And so we'll let the right edge slide back and forth, and it can move. So here we'd have an area. And then we slide it a little more, we'd have a new area. And we slide it a little more, We have a new area, right? So we can make a table where x would be the right edge of the integral, and then our output would be the area that's created. Now, think about what our integral will look like then. Our integral is going to go from 0 to x, right? Because that's an unknown. Our right edges are unknown. It's going to be changing. Okay, so now we're going from a fixed piece of area from 0 to 1 or 0 to 2 or 0 to 3 to a changing value. Okay, but you see how that would create a function, right? The input to the function is the right edge, and the output is the area that's created. All right, so we can give that a name. We could call that, say, A of x, A for area, right? Now, in here, now this is the part I told you earlier today where the notation gets kind of weird, and we'll have to just, get comfortable with that as we go. In here, what goes right in here? The function that I'm doing the area under. So little f. The problem is I can't call it little f of x because I'm already using x for this. And I can't use x for two different things. So we're going to just change it to something else. Change it to t. Now, that shouldn't really bother us because remember, we've said all year long, if f of x is x squared, then what's f of t? T squared, and f of u is u squared, and f of w is w squared. It's the same thing. It doesn't matter what letter you're using. So whatever this little f function is, if this little f was x squared, when we put it in here, we would put in t squared or something else. Usually they use t. That's what they usually use. They'll use x up here and then use t in here. Okay? So I don't want you to get too messed up with it. It will mess you up for a while. X is this variable here, matches this variable here, right? The input of our area function is this right edge of our area. This variable in here doesn't really matter. It's just there. It could be anything, as long as it's not it. Okay? All right. That sets the stage a little bit for what you are about to do here. So, what this calculator document I'm going to send you is going to give you a little f function. You're going to slide that right edge to various values, and it's going to tell you what your area is, and you're going to fill in that table. Then you're going to plot those points, and you're going to look at it, and you'll see what's happening. And you're going to do that for a couple different functions, and you're going to answer some questions. Hopefully, you kind of see some cool things happen. Okay? So I'm going to give you this worksheet now. And I'm going to send you the document on your calculators. All right, Jacob, thank you for your presenting today. You did a fine job. Oh, I did send it? Yeah. Oh, you already got it. Okay. So, this right here, Introduction to the Fundamental Theorem is what we're working on. I think you end up, it has you start here on this page right here. And so it starts with just a constant function. It's going to have you slide this point. Now, you can go ahead and get into groups if you want. Now, we're going to get out of those groups to talk about it later. But if you want to get with a partner or 2 or 3 and work on this, we'll probably take 10 to 15 minutes for this. Okay? Go.
What's it called?
Introduction to Fundamental Theorem. Oh, is it just Fundamental Theorem? Okay, it's just Fundamental Theorem. I guess. Yeah, it is just Fundamental Theorem. Yes. What? Click that point. When in doubt, hit escape. You just slide it. You grab it, you click on it. Click and hold. Click and hold. The true value. Now the integrand remembers the function inside the integral. The true value? I guess I don't know. Where are you at? No, it says what is true of the integrand at these values. Yeah. Couple more minutes.
The integrand's the function, isn't it?
The thing inside the integral, right? The function you're doing the area under. All right, let's go ahead and move your desk back to where you were. I know you might not be completely finished, but that'll be a little part of your homework. Not a lot of homework tonight. It's full of important concepts, but it is not a lot to do. But anyway, let's move on back, and we'll talk about this a little bit. See what you're coming up with. and try to wrap up at least today's portion of it. Move the desk back too, if you would, please. All right. Now, okay, so you had the first graph, which was a horizontal line, and as you moved that right edge, you kept getting a bigger area and a bigger area because you keep picking up a new chunk of area, right? And so you graph it, it was a line, right? Wasn't that true? And then on the second one, where you had a line, kind of like this, I've kind of duplicated it here a little bit. You had a line and you do the area under it. Now, every time you move over, and I heard a group talking over here about every time you move over one or whatever, you pick up another chunk of area, right? But what happens to each chunk as you move over? You add bigger chunks of area, right, each time. And so your area is growing, but increasing at an increasing rate. We've heard that before, right? Might be exponential, might be just a parabola too, right? I mean, but it's growing at an increasing rate. Concave up, right, would be the situation. Now, I've kind of mimicked that here with a different program. This dot right here is plotting the area, because think about what we just talked about wanting to do. We want to create an area function. So every time we get a new right edge, we get an area that goes along with it. And that we could plot. We could plot those pairs. We could graph the area function and look and see what we get. So I've got that here. I've got this yellow area is about 8. This dot right here at the right edge, input, the output is the area. There is that dot. Now, if I slide this right edge back to the beginning, what area do we have right here? 0, so the area is 0. As I go this way, I'm picking up bigger and bigger chunks of yellow area. Pick up more yellow, I'm adding more area. The area function is going up, 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 and it would continue to do that forever and ever and ever. Now, here's where it gets really interesting. Let's say we slid the right edge past the left edge over to here. Now, it's still the right edge. This is still the integral from 0 to x. Well, if we go from 0 to x, that's backwards. What do we know about the area when you go backwards? Well, not negative. Opposite. Opposite, right? What is this area down here normally? Negative when it's below the x-axis. But if I'm going from 0 to x backwards, this area is actually positive, right? Look at the area. Right here, it's positive. So therefore, I guess I lost my point, but right back here, it's positive area. In other words, this picture here, and remember my integral is from 0 to x now. There will never be any negative area in this picture. Now that seems strange because you think this is negative. No, it's not negative. Why not? Because it's 0 to x, and in this case it's backwards. So when we talk about the right edge, x is the right edge, we actually can have that right edge go over and become the left edge. We're actually going backwards, right? But the integral is defined to be from 0 to x. All right, now, in the back of that sheet, the very last question, you started answering some questions about minimums and increasing and decreasing, right? It started asking about when the area, well, it said the value of the integral was decreasing, or when the value of the integral was increasing. Well, the value of our integral is our area. So let's talk about when our area is increasing and when our area is decreasing. Now, right now, whenever we talk about increasing and decreasing, we always talk about going from left to right. Okay? So let's start over here and let's move this way so it makes sense. So we got an area, I can't even see it on the screen right now. It's this yellow area. Now, what do we say about this yellow area? It's what? Positive. This area is positive right now. As I slide this X to the right, what's happening to my yellow area? I'm losing it, right? I'm losing positive area. Well, if you lose area, what's your area graph got to do? Go down. Here it comes. It's going down because I'm losing positive area. It is going down until right here when I have no area. Then what happens? I start picking up some positive area. So my area graph goes back up. So my area graph was decreasing over here. Why? Because I was losing positive area. Now remember when I used to talk about there's two ways to talk about decreasing? You can either get less positive or more negative, right? So can you imagine a scenario where a graph could be decreasing in one of two ways? Your area graph could be decreasing because like here we're losing positive area, or we could be gaining negative area. Couldn't you imagine a situation? Maybe if we had a line going down like this and we slid this way, we'd be picking up negative area, and that would make the graph decrease. Think about some of these connections of things. This is what I think is so cool about this, that we did all of these things about slope, and we came up with all these tons of connections, and now we're moving on to talking about areas. This doesn't have anything to do with slope, right? Not the slightest bit to do with rate of change or anything. We're talking about areas, and all of a sudden, all of these same kinds of things are coming up again, okay? Now, I've got another picture here where I've got this F graph, little F graph, and I've got, again, some area. This time my left edge is over here on the left side, the A, and I'm going to slide my X. And again, I'm picking up some area here, right? Picking up, what is this yellow area? Positive or negative? Picking up some positive area. But starting here, what happens? Well, because I start picking up negative area. So my area graph would start going down right now, right? And now I keep picking up negative area, right? All this area I'm picking up right now is negative area. So my area graph's going down, 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 down until here. Then my area graph's going to start going up because I'm going to start picking up positive area. Switch from negative to positive. My area graph was going down, now it's going up. Wow. Sounds very familiar. All right, picking up positive area. Okay, I hear you saying things, but I don't know what you're saying. All right, so now, where am I at? Back to this. So let's do this problem right here. So yes, some of you are talking about derivative and antiderivative. I don't know, maybe something. But we're going to figure it out. Write down this problem right here. You already got it figured out. Good, good, good. There's connections, for sure. There's connections going on. And to be honest, and I know you guys are seeing it. Well, wait till you do this. Man, we got to hustle. We got to go. All right. I hate to just blow your mind and then turn it loose on the fourth block. All right, but let's look at this function right here. Let's look at this function right here. Now, okay, just like we've been talking about. It's area function, A of x. Okay? We're calling it A of x. Our input is x, which is our right edge. As we can see there. From 2 to x. Now, I want you to copy this down because your very first homework problem today is almost a carbon copy of this problem. Okay, so you would use this as your guide for your homework problem. Now, here's our function, t plus 3. Now, really, that's the graph what? Y equals x plus 3. It's really the graph y equals x plus 3. We call it t plus 3, right? Because we have to put a t in there because we can't use x for two different things in that problem. But it's really the graph of y equals x plus 3. So let's come over here and let's graph y equals x plus 3. Okay, slope of 1. Yours doesn't have to be real fancy or anything. Okay? Just give yourself a line. Okay? Like so. And we're going to do this, and we want to do the area from 2, that's going to be our left edge, to x. Now, where's the x? We don't know. It's over here somewhere. Remember, this x can slide. I want you to have in your mind, when you're doing these area function problems, I want you to picture that thing I just had up on there where I was dragging that back and forth, and you were seeing the yellow area in there. That's what I want to be in your head. Okay? So in this case, I'll make that area red, but I've got some area here. Now, since I chose that to be a line, that is a trapezoid there. Now, I don't know where that right edge is, and could I drag it over to the other side of the two? Sure. We saw that already. Let's make it easy on ourselves. Let's keep it over there. Okay? Now, I want a formula for what a of x is. Well, yeah, let's just do what we've been doing. The only difference is we don't know a right edge. We're going to call it x. But otherwise, it's just what we've been doing. So 1/2. Now, what is this base? 5. We got to plug a 2 into our little line function, right? Plug a 2 in. 2 plus 3 is 5. So this would be 5. Plus, what's this side then? That's a tricky one. Yes, that's just x plus 3. Exactly. We don't know what it is because we don't know what x is. So we just plug an x into the line function. Oh, x plus 3. So that is that edge. And then times, what is our height here? Wouldn't that be x minus 2? I mean, if that was a 7 there on the right edge, it'd be 7 minus 2. It'd be 5. So it's x minus 2. All right. Oh, okay, so we got a little work to do. So this would be x plus 8, and this would be x minus 2. Oh, I got to FOIL that. Okay, that would be 1/2. This would be x squared plus 6x minus 16. Did I do that right? Oh. Multiply by 1/2, what do we get? That's our area function. Isn't that awesome? No?
Yeah.
Okay. Your homework. Finish that worksheet. This is in section 5.2. Number 2 is just like what we just did there. Okay? Similar. It changes one piece of it. Well, a couple pieces of it. The function's a little different. The little f function, the one you're doing under the graph, left edge is a little different, I think, but you go through the same process. Okay? Then we're going to do 3 through 8. Now that's a section that, again, is talking about an area function. It gives you a graph of a little f, and it asks you some... Oh, by the way, I got a little more to add to that, so hang on a second. If I give you this function, and I ask you, what's a of 5? What am I asking for? Plug 5 where? Right, this x matches that x. Again, that's why we can't put an x in here, because if we put a 5 in for x, we'd have to put a 5 there, and then that would change everything. Then it would be just an 8 there, which is a horizontal line. So that's why we can't have x here and have x here. So if I ask for a of 5 with this function, put a 5 there, which means put a 5 there, which means a of 5 really is saying the area from 2 to 5. The area from 2 to 5. Okay, just so you understand that notation. All right, so that's section 3 through 8. And then we're going to do 9, 10, and 11.
Why don't you just do 2 through 11?
I was waiting. Why did I know it would be you that would come up with that? The other class, I gave them this, and then I looked at it, and no one said anything. Of course, they got quiet anyway. And I said, oh, why didn't I just say 2 through 11? And I said, I'm going to give it to the other class the same way and see how long it takes somebody to notice. And sure enough, he looking to catch me on something. Always. All right. But yes, it is 2 through 11. But 3 through 8 is kind of a separate section, and then 9, 10, whatever. But it is 2 through 11.
How do you do it? Is that it?
I don't know. That's it. So, yeah, very short assignment. We just did it. We had it. They don't even know yet, I don't think. I'm not sure they got it.
They didn't realize it?
No, I think they did. They did. Allie did. Allie had to fill it.
Carly got it.
Carly had it first. Carly had it first. You guys had it when you were doing the worksheet, probably, right? Kinda.
Did he tell you to wait?
Even before that. Well,
Not catching it?
So exhilarating.
well, actually, the very first day when we did that velocity picture and we said the area under it was position, right? We did the velocity graph, the area under its position.
Yeah.
So we already kind of knew, we already kind of knew it was anti-derivative. But when you see the actual anti-derivative just show up
You get real excited.
out of a
You were getting
trapezoid,
excited.
it's like, are you
See,
kidding?
that's what I heard. I never saw this lesson. I missed this lesson.
I feel like you knew.
I
that
don't
was
feel
already
too upset because I was in
happening.
the Bahamas, so it wasn't a global thing. But I missed this lesson. When
Yeah,
I
they're,
got back,
they're going to tell you, don't feel bad.
they said, you missed this part. It was amazing. Maybe he's calmed down a little bit.
I probably have. I've gotten old and jaded.
We still don't play Pictionary.
That's because you're not a good class. You're in bowling league tonight?
Yep.
That's it.